Just 1 second, it'll just start broadcasting and then. Yeah. So I guess like your first question, I think, was kind of like that. So if it's like, what if I have two strings, or like not string, but like something like this? Uh, so here I made it so that S2 has enough space, right? So in this particular case, if you initialize like this, there is a null character automatically, right? But you were asking what if it happens to be an array of characters and you don't know the length. So if you don't know the length, there's nothing you can do because you don't know where it ends. If you do know the length, so if you know that like length 1 is whatever 6 and length 2 is 3, then you can just say, something like this, right? Uh, if you want it to end with an null character, then you would do this. And does that make sense?
Yeah.
So you could also, I think what I said is you can also use memcpy. So you can say memcpy to S2 plus length 2 from S1 and copy this many characters. So what this does is it just says like copy this many characters from source S1 to destination S2 plus length 2. So that's the same as this.
Would it always be safer to use memmove instead?
So the difference between memcpy and memmove is that memmove works if there are overlaps between the source and the destination. Now, if there are overlaps, like in this case, I think doesn't even really make sense to say like what if there are overlaps. I suppose it could happen, but it's difficult to imagine a scenario where you would use it. But you're right, like there's no harm in using memmove rather than memcpy. It's like marginally slower, but like in practice it doesn't matter.
Okay. And also for the first line, like line 5, if you instead like for line 5, there's a null character, right?
Yeah.
So then what's the difference between that and car star S1 without the square brackets?
Yeah, so not the null character, which would be there either way. The
Mm-hmm.
difference is that one is an array and one is not, right? So this is an array, so it's initialized like this. But really, what you mean by this, it's you're declaring S2, and then you're saying like S2 at 0 is equal to X, and
Oh,
S2 at 1 is equal to Y. So this is just shorthand for this.
okay.
And that means that S2 is an array like any other array. So in particular, it would be a local variable. So you cannot have like a function where you do this and then you return S2 because the local variable is not valid anymore after the function finishes running. Uh, this is different because what this is saying is this is kind of like Python, like the Python string, right? So it says put XYZ somewhere in memory and then make S3 be the address of the X.
Mm-hmm.
So that means that you can, for example, return S3. That would be fine. You can access on the contents of S3 outside the function. It also, in particular for C, means that because you're not actually allowed to modify strings that are defined as string literals, that you cannot go S3 at 0 is equal to a capital S.
Okay. Um, so then when would you ever be able to change a string? Like other than if it's just in an array.
So a string is a sequence of characters with a null at the end, right? So it's about how it's created. So if it's an array, you can change the array. If it's a malloc allocated block, you can also change it, right? So if it's like this, that's completely fine.
So if you malloc a string, it's
Well, you're
you're
not
mallocing.
mallocing a string, right? So again, kind of the vocabulary, and I think it's like better to use that vocabulary, even though of course like, you can use any words you want. So
Mm-hmm.
a string is just characters with a null at the end.
Right.
So and then the characters with a null at the end can be stored in different ways. So they can be stored in an array. So
Mm-hmm.
think like this, or they can be stored somewhere in memory where if you put a string literal on the right-hand side, not initializing an array, but putting it on the right-hand side and assigning it to S3, stored somewhere in memory, and then S3 here, just the address of the X.
Mm-hmm.
Or it could be that you malloc a block of memory, and then S4 is the address of the first element in the block, right? And
Okay.
you are allowed to modify the contents of malloc allocated blocks, and you're allowed
Mm-hmm.
to modify the contents of arrays, but you cannot modify the contents of a string literal as defined this way.
Okay. Um, um, would it like would it be different if you did car star constant or
Uh,
something?
yeah. So this is kind of a slightly different aspect of it. So if you say something like this,
Mm-hmm.
so this is like not so this is kind of not super interesting because if you do this, so this would be not allowed and would not compile.
Mm-hmm.
Whereas this is just not allowed, but it would compile. So the difference is that the const basically saves you from doing things that you're not supposed to do anyways. So a situation where it's a little bit more subtle would be if you do something like this. So this kind of looks fine. So this would not compile. And then if you define, so here we have S2 that you're supposed to be able to modify. And then if you do something like this would not compile, but would compile and run if you remove the const on line 22. So in this situation, what you're doing is you're specifically constraining yourself from doing something that would actually work.
Okay. Even if you didn't have the const and then you put car star S and then when you called the function you use S3, it would still also not compile, right?
Sorry, I don't quite follow. Could you repeat?
Sorry, if you called like the function and then in the brackets you put S3, it would also not compile?
You mean
Or
like
like outside the like
uh
if you just called the function.
like S3 here?
Yeah.
Yeah. So here that okay, so let me just do a different line. So S3 here, so that still would not compile because like this by itself would not compile separately from anything else because you're saying I'm not supposed to be modifying the content of S and then you do that. So then would not compile is here. So this also would not compile
Mhm.
and then would compile but potentially crash if you remove the constant line 22. Right.
Okay, that
So
makes sense.
that So that's because you're not supposed to be modifying S3. But if you don't constrain yourself from doing that explicitly, then it would compile, it would just crash when you run.
Okay, that makes sense. Um, Also, my next question is, what's the complexity of QSort?
Um, so it's a little bit complicated because the worst case runtime complexity of QSort is O of n squared.
Mm-hmm.
However, on average, it runs in O of n log n. So we have not done that kind of analysis in class. So usually the worst case complexity is like what you care about because the average is basically determined by the worst case. In
Mm-hmm.
some specific cases, so those would be quicksort and things that we mentioned briefly with kind of dictionary access of dictionary elements, stuff like that. In those particular cases, the average case complexity and the worst case complexity are actually different. So this is not something that we've done in class, though.
So for, I think it was like 2024, there was a question on, I think, or it was like find the median, and then I did like QSort to then like sort it and then find like the middle value.
I
And then
believe it was let me see. Uh,
this is 180.
yeah, and then I asked for the complexity, right?
Mm-hmm.
Uh, so yeah, I mean, kind of the straightforward answer is that I did not mean for people to use QSort, and then like if you don't know the complexity of something that you're using, then like you just see that part B asks for it, and it's just like like you should be strategic about like not getting yourself into a situation where you don't know the answer. Uh, yeah, so here, like I suppose because technically this does not say worst case time complexity, we would have to accept both kind of n log n and n square as the answer.
Okay.
Uh,
Um,
that's just like actually bad wording. I should have said worst case.
okay. How would you
Like
do this
we would
question?
accept n log n and n square. Yeah.
How would you do this question without using QSort? Like, would you have to use another sorting method?
That's one possibility. I think if I were to try to do it in the most straightforward way, what I would do is I would just go through all the elements of the array and ask like, is this the median? Is this the median? Is this the median? Is this the median? And then like is median would be just like counting how many elements of the array are smaller or equal than the element that you've chosen.
Oh, like having like, oh wait.
Just like literally like, for I equals 0 up to n, like
Mm-hmm.
count how many elements in the array are smaller or equal than array at 0, and then count how many are smaller or equal than array at 1. And if at any point you see that there is n over 2 elements that are smaller or equal, then array at I is your answer. So, I mean, there's multiple valid ways, but like this seems to me like the most straightforward.
But then how would this cover like if there was like an even number of and then
It,
you had to take the average?
it doesn't matter. Like you just need to know like how many are greater or smaller, and then just like like if they're different by 1 or if they're different by 0, then you know that that's the answer. I think strictly speaking, it said that you just have an odd number of integers, so you don't need to worry about like an even number.
Okay. Okay, cool.
So like what you might worry about is like what if they're all equal or something. So
Mm-hmm.
for that, so then like any one is the median. So yeah, like you would want to count like how many are smaller equal and how many are larger equal. So So then you would have kind of like if there's like the same number of small equal and larger equal, then you have the answer.
Mm-hmm. Okay. Um, Also, yeah, so for I think a question here, there was like a question about like rearranging the order of words.
Mhm.
Um, I think you use dynamic programming, but I'm not
Yeah.
like not sure when to use dynamic programming.
Are you asking like in general about this specific question?
In general, but also not this question. It was I'll try to find it. Oh wait, never mind. It was no, wait. Sorry. Question 3 of 2024.
Okay. Oh yeah. Oh, I see. Yeah. No, this is not really dynamic programming. This is just looking at like basically do you have in your mind like how to reverse a string, just like make make the letters be in the other kind of from right to left.
Oh, okay.
So this is kind of the same, except you do it with words, right? So like the way I would think about it.
Hmm.
So like if it were Python, right? So you would just say you would just say split, and that's like A, B, C, D, F, X, Y, Z, right?
Oh, okay. Yeah.
And then you would like reverse it, right? And then so technically there is a way to do it with a one liner, but I won't. So I'll say like words, and then I'll do like so like something like this. Does that make sense?
What's strip?
So this just removes like the extra spaces on the right and the left, if you remember.
Oh, okay. How
So
does, sorry.
yeah, so that's like Python. So like there is a way to do the same kind of thing in C, but it's kind of complicated. So the way I would think about it is like you have like X, Y, Z, D, F, A, B, C. And then what you want is you want to like go to the left and then copy ABC and then go to the left and copy DEF and go on the left and copy XYZ, right? So you would say, um, you know, so stop. So I would say like J is this, and then I would say like, so while J is greater or equal to 0, so what I'll keep doing is I'll keep going back until I encounter a space.
Mm.
And then when I encounter a space, I read to the right and copy it. So I'll do so same length. And then I'll do like while I have not encountered a space and I haven't gone uh kind of to the negatives. And now I copy the word. So make it like a little bit clearer. I also solved that, I think, in one of the other sessions.
Okay.
Kind of like this. So that's bad.
So you would just remember where your last space was and then keep on going to the left
Yeah,
and then
exactly. Yeah. So my last space is my last space is on J,
Mhm.
and then I subtract one from J and keep going. So this is not so I guess the way to think about it, so I think your original question was like when do I know when to use dynamic programming?
Mhm.
And the answer is basically dynamic programming would be when you're asking kind of whether something is possible or when you're like looking for the small this and like you never know like in this class you know that like basically if it's something that looks complicated then it is quite likely dynamic programming. You never know whether like the dynamic programming technique would work or not, but ordinarily it's like when you're trying to find like the kind of optimal solution for something, or if you're trying to build up a solution where for smaller numbers it's possible to kind of solve it directly, but for larger numbers you need to rely on decomposing the problem into smaller parts. Here it's not really that. Here it's basically like taking an input of length n and transforming it to an output that's the same length. So that's quite unlikely that you could see it in terms of dynamic programming.
Because originally I thought of it, which is maybe kind of stupid now, but just like going from like just taking a string and then basically splitting it into words and
Mhm.
then basically just like say, oh, go from left to right. And then if you encounter a space, then like take that element out, but then like add it to like say an array and then call the function again on the rest of the string. And then that like splits the string up into words.
Yeah.
And then I basically would have an array of words and then just rearrange it somehow
Yeah, I mean, and that's possible to do. It's just that it's quite annoying to do in C because
because of like,
because like a string is like a pointer, so you would have to have an array of pointers.
mhm.
So like it's totally possible. It's just like not the easiest thing.
Okay. Um, okay. So definitely go easiest
I
possible.
mean, that's what I would do. Yeah.
Also, I had a question on like 2D arrays and
Okay.
how you would construct like malloc a 2D array.
Okay.
I
Uh,
was wondering.
so yeah, so so that's essentially kind of quite related to what we were just talking about, right?
Mm.
So uh so we want like a 2D array. So the usual way that you would do it is you would just create a flat array and then you would index into it. So if you want like n by m, you would just say, we'll create a flat array. So we'll just like, does that kind of make sense, or do you want more elaboration on this?
So is it like um
So it's kind of we're saying it's really a flat array, but like this would be like 0, 0, and then this is like 0, 1, and this is 0, 2, and this is 1, 0, and so on. So something like this, right?
Mhm.
And then we're saying to access ij, we need to skip I rows and then go j to the j elements to the right. Right? So to skip I rows, you need to skip this many elements, right? So that's this part. And then to go j to the right, it's just plus j. So that's why it works, right? So you just access this kind of thing. So that's kind of the way you would more usually do it. I think what you are asking about, though, is kind of a pointer of pointers, like a pointer to an array of pointers. So you could do it like that, right? So you could say, I want I want I want an array of this many lines, and then for every line, you would say, okay, so like array at I is this much, right? So, and then array at I is a block of memory of this size. And then to access elements, so this would be array ij, right? And the logic here is array at I is just this guy. And then this guy is just an array. So like once you have array at I, so this is an array, and then you go and get the j element.
Okay. Um, okay. Is also for like functions and like the input parameters, would this be like int star 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 array?
You definitely, so there's two situations, right? So one situation is if you create this and then you just want to, let's say, print it out, right? And in this case, no. So you'll just say this,
Mm.
and then here you would just have, a nested loop. That's completely fine, right?
Mm.
So does that make sense? So because like you only need to access it, and then like when you call print array, like if this is a pointer to a pointer to end, then this is a pointer to a pointer to end. That completely makes sense. So a different situation is if you want to create it. So if you want to create it, it would be like this. And the reason it would be like this is that when you're calling it, you would say like int star array, and then you would say create array, address of array, and that's because you want to modify the value here. So in here, malloc returns the address where you store this, and then you want to modify this variable, or like the value of this address rather, so that this guy gets modified. So anytime you want to modify a variable, you need to send its address. So if the variable initially was in star star, then the pointer to it would be in star star star.
Would you be able to like remove the first parameter and then create this matrix or like 2D array inside the function and then
Return it.
assign and then like instead of void it would be
Yeah. So you could do that. Yeah. So that would be like in star star. So something like this, and then you return it totally. Yeah. And then the way you would call it is you would say something like this.
oh yeah. So that would also work.
Yeah.
Okay. Um, do I have any other questions? I think I had a question about like the linked the adjacency list and the
Okay.
linked list.
Mhm.
I don't really recall what my question was. Sorry, give me a sec. Oh wait, not a question about that, but another question. Um, if I had a list and I wanted to like append to the list
Mhm.
uh through like dynamic programming, would that be memoization?
Uh, I mean, so not really. Memoization specifically refers to uh, having a function rather than compute the result, check whether the result had been pre-computed, and then just return the pre-computed value if it has been pre-computed. So like that's what memoization is. It's like this mechanism in the function where you check whether you already computed the answer, and then if you already had and you restored it, you just return the pre-computed value.
So we did it for the painting the houses, right?
For multiple, so those are like separate things, right? So like the simplest thing with memoization is like just like Fibonacci, right?
Mhm.
So just like something like this, right? And all it is you're just saying, like if you already pre-computed it, just return the pre-computed value. And then stored. So if you hadn't, so you haven't returned, so then you pre-compute it for next time, and then you return whatever you just computed. So that's what memoization refers to. So anytime that you have a function, you can memoize, right? So it's just a question of whether it actually makes sense or not. So memoization makes sense if it's likely that you would call the function again with exactly the same inputs, right? So a lot of the time when you're doing dynamic programming, it does make sense because in dynamic programming, you like repeatedly try to compute the answer for like small inputs, right? And there's few possible small inputs, so it's likely, in fact, it's gonna happen usually that you're calling the function with the same arguments several times. Um, you could imagine a function where it's not likely. So like for an example of that kind of function would be like, like multiply, right? So,
Mhm.
you know, could be anything. So, or at least kind of in the general situation, like you might like to multiply, all sorts of things. So it doesn't really make sense to like store, 123 times 525 just in case you need to compute it again, because
Right.
probably.
Yeah. Okay, that makes sense. So would you always use a dictionary and not a list?
So dictionary access is average time of one. If
Hmm.
you use so you can use a list for that if you know ahead of time how many possible inputs there could be. But like the dictionary is easier because dictionary would work always. List you have to think about. List is good if you like, so this is just like implementation considerations, right? So like if you have potentially very large inputs, then like if n could be like a billion, then if you were to store the answer for everything, then a list would need to be a billion integers long. So that might take up space. So that's inconvenient. So in Python, where dictionaries are easily available, there's no reason not to use the dictionary. In C, there is like a very good reason not to use a dictionary because like, you actually don't have dictionaries like available in C by default. So you kind of have to use an array.
So or no, I guess would a like the equivalent of a dictionary be a linked list or no?
No. So linked list, worst case lookup in a linked list is all of n. So that could be potentially very slow.
The
So,
same as like a normal list.
no, not exactly. And what do you call it? Normal list is an array. So in an array, access time is of 1 because you can just compute like I need to skip. And so if you need like access at the mth index, you just skip m places and
Mhm.
so access time is O of 1. However, insertion time is O of n because if you want to insert at the start of the array, you need to move all the elements one space to the right. So that takes O of n time. Dictionaries are like O of 1, both access and write. So we have like I think like third lecture before last, or like I guess fourth lecture before last, we briefly talked about one way to implement dictionaries, which is with binary search trees. So with binary search trees, we talked about how if the tree is balanced, then access time is of log n, which is like not quite of 1, but still pretty good.
Mhm.
And then we did not get around to actually talking how you would write so that it's of log n as well, but it's possible to do it in of log n.
Okay. Okay. Um, cool. Also, what would a potential question, not that I'm asking you to give me the question, but like, how are the questions revolving around like the AI part that we did in like the last week? How are
Mhm.
those going to be like structured or like what's
So yeah, so you can look at like the Friday office hours session. So we did like a number of examples there.
okay.
But basically like what it could be is like the need to know slides, right?
Mm-hmm.
Would be like uh here is like a specific format in which the data is, implement the need to know algorithm. And there, like, I know it might look kind of intimidating at first, but like none of those algorithms are actually difficult. Like they're like literally like one for loop usually. Uh,
Okay.
so what you need to know is like which for loop essentially.
Okay.
Uh, so yeah, so like we solved, I think we solved like basically all of them during the Friday session. So like if you scroll around on YouTube, then like there's examples.
Okay. I'll go do that after this. Um, Another question. If I were to do like dynamic programming and say I wanted to like add um like numbers to a list,
Okay.
uh, but I wanted to do it like with like memoization,
Mhm.
um, how would I
So
do
again,
this?
like memoization is literally just this.
Okay.
So like this, so that, like that's this is just like specifically this where you check whether the input n is already stored in the dictionary, and then if it is, you just return it. Like that's all it is.
So but it's like also you're keeping a list of everything you've computed in the past.
Well, a dictionary in this case, but yeah, you could do it with a list. Yeah.
Yeah, like a dictionary list. So then if you create like can you do okay. I feel like I'm just talking in a circle. Um, yeah, I don't know what I'm even asking.
Yes, I think you're asking about kind of related concepts, kind of memoization and dynamic programming. So they are related, but the way in which they are related is like on a conceptual level, right? So you could implement Fibonacci this way. You could also do it this way. So you could say like, so you could also do this, right? So in a way, conceptually, they're similar in the sense that in both cases, what you're doing is you are like computing fib at 2 once, and then fib at 3 once, and then fib at 4, fib at 5, and so on, right?
Mhm.
So they're related conceptually in that way. But uh, like this is what you would refer to as dynamic programming in the sense that you have this list and you're just like first you compute like fib 0, 1 and then fib up to 2 and then fib up to 3, fib up to 4 and so on. And the way you're doing it is by referring to previously computed values. And it's kind of the same here where like you compute fib of 2 and then you can compute fib of 3 and then you could compute fib of 4 and so on, right? But in a way, there are kind of different techniques, right? So here you do it recursively here, and it happens that you compute a fib of k just the once for every k, just because the next time you'll just return the pre-computed value, right?
Mhm.
And here you're like the formula is the same, like this is the same as this, right?
Mhm.
But here you're just explicitly growing the amount of stuff that's been computed.
So for the second one, it would be, or the first one, it would be O of n.
They're both all of them. Yeah.
They're both. But don't you compute everything like multiple times for the second one?
For the
Or
set, no, the other way, like if anything for the first one, right?
or like the normal fib recursion?
Which one is the normal?
Um,
So this is kind of straightforwardly O of n, just because it's like a loop that runs approximately n times, right? Here, it's kind of like you have to think about why it's O of n, right? So the way the tree would look is you call like fib of n, and then fib of n is going to call it's going to call fib n minus 1, and it's also going to call fib n minus 2. And then this is going to call fib n minus 3, and it's going to call fib n minus 2, and so on, right?
mhm.
So, but the thing is, so like the order in which those things happen is like fib n calls fib n minus 1, calls, sorry, this is n minus 2 actually. And this is minus 3. So the order in which it happens is like this calls this, calls this, calls this, calls this. This guy waits around until this guy returns, and then it calls this. So what's going to happen is you will call fib n minus 3, but the next time you need fib n minus 3, it'll return right away, right? So when fib n minus 4 calls fib n minus 3 again, so this makes no sense. This is n minus 1. Uh, so uh, so when fib n minus 1 gets called over here, it will return right away. And that's because fib n minus 1 will have been computed here first. So this tree is going to basically look like 2 calls here, 2 calls here, 2 calls here, 2 calls here. So n times 2 calls in total, if that makes sense. Sorry, that was a little bit messy.
No, yeah, that makes sense. So in 180, we did it as if it was like go left and then also go right, and we didn't like do the like
Memorization, yeah.
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 So that Like, what's the time complexity of that? I thought that was like log n or something.
No, no,
Or
it's much more. You can look. So that was like the very last lecture in 180 if you want to look at that. So the upper bound on that was O of 2 to the power of n. And then it happens that there is an exact computation and you can show that it's like O. So without memorization, it's O of fib of n actually. And it's kind
oh,
of like it's like maybe like not relevant to like your life directly right now, but you can look at the last lecture for 180 for the explanation for that.
okay. Okay, thank you.
Sure. Ellie, yeah, so so I would refer you to the Friday office hours YouTube. I went through Q6 and Q7 there. It just like takes a while, but like if you've seen it and you have a follow-up question, I'm happy to answer.
Okay, thank you. I have another question about linked lists,
Okay.
kind of in generally. So is it like there's like three components to a node, the address, the value, and the next thing?
Yeah. Yeah.
Okay, so it's not like okay, and then for the head, it would be like the value of the head and then the next component and then also the address of the head.
I mean, it depends on how you implement it. I believe we did not have the value in the head, so we just had like so we had basically so like there's several ways to do it. So the way we usually did it is we had a node that looked like this,
Mhm.
and then like something like the value, and then you have like the next,
Mhm.
and then we also had like a linked list. And then it just had the head and like whatever else you want as well. And then it so here we just had like like you just access the first node by looking at head, right? And then like the value of the first node would be like, so if you have like, and then you would do like LL1 head data, right? So LL1 head would be like a node. And then for any pointer to node, you just get the data at that node.
Okay. So it's not like the address of the head is the address of the value of the head?
So the value of head is the address of the first node, right? So it's like,
Oh,
so
okay.
you have like the nodes and like the nodes are like, so like let's just like make up addresses
Mhm.
and like maybe they're not like sequential, right? And then you could have a value that's like whatever, like 42, 43, 100, 50, 200 or something. So this is like data. And then next could be something like this, right? So the way so here I just like made them so that they kind of display nicely in a rectangle, right? But like,
Mm-hmm.
so the first node might be stored at address 1000, and then at that address you store the value 42, and then also the address of the next node, right? And then at 1060, it happens that the address of the next node is like 2000,
Mm-hmm.
right? And then you could also say like head, that would be 1000, right?
Oh,
So head would be like the address of the first node.
okay, that makes sense. And also, would we ever be required to write like depth first search and like the different graphs in C?
I mean, it's happened before.
Okay. Okay.
So it's I did it. So I did an example like that in yesterday's office hours. If you want to look,
Okay.
it's a little bit annoying to do because so depth first search less fill than others, because depth first you could just do with recursion. So that's like not that difficult. If you want to do like breadth first, you have to implement a queue by yourself in C, which is kind of annoying, but like not impossible.
Right. Okay.
Because like so like implementing, so you can look, I've implemented it in yesterday's office hours. It's not
Mm-hmm.
impossible, but it is kind of annoying, and like I reserve the right to annoy people on like at least one.
Oh,
But yeah,
okay. Um, Also the like I know Ellie asked this, number 6 and number 7,
yeah.
why is it so long?
Are you mean like the solutions?
Yeah, like
Well, I mean, like part of it is like there's comments everywhere, so like it could be twice as short.
okay.
But it's not like, yeah, like it was like, to be honest, I like so like I did intend for them to be difficult. Uh
Mm-hmm.
I did not quite intend to for them to be so kind of as difficult as it turned out to be. So it was like a valid question to ask, but like in retrospect, I should not have like I should have definitely left question 7 out of the exam. It's like barely anyone solved it.
Right. And then I thought like A star was just like adding that like last part to the depth first
Yeah,
search.
it is. Yeah.
But then you have to like find the like how would you find the minimum distance if it were not like on a plane? And then you can just like find the coordinate distance.
Yeah, so that is kind of why I put G7 on the exam, as like an elegant way of doing something that's not a distance on the plane. So there kind of the nodes are game states in game of 21, which is like just like the sum at which you're currently at, right? And
Mm-hmm.
then, like if you want to get to 21, then a straightforward way of figuring out whether you're close or not is just like 21 minus the current
Oh.
score. So if it's small,
Mm-hmm.
you're probably close.
Okay. So you just determine yourself what you want like that heuristic function to be?
Yeah. Yes.
Okay.
I mean, like it might be good or bad, but yeah, like essentially, like so kind of a heuristic means that you you don't know the exact answer. You're just trying to approximate it somehow.
Mm-hmm.
And
Okay.
yeah, like that's like problem specific. It's not super easy to come up with like diverse examples where it actually works. But yeah, like this is why like I came up with it specifically. I was thinking of like, like where can you figure out a heuristic that's like not that difficult to figure out. So like specifically, like if you're trying to get to 21, well, like how far away from 21 you are is kind of a good heuristic, right?
Mm-hmm.
Uh, but yeah, like it turned out to be difficult in other ways that I did not quite see when I was putting it on the exam.
Oh, okay. The like response, like how many percent of the class got it right? Six and seven.
Um, I honestly don't remember, but like less than 5%.
I think that makes me feel better. Also question about priority queues and Dijkstra. Um Dijkstra, like the main reason why it works is because of the priority queue, right? Kind of.
Um, I would say that I would say like works in the sense of it returns the correct answer. No, you could do it without a priority queue. Uh,
Mm-hmm.
so it so kind of the priority queue where on queue and DQ are of log n are the reason it works like in a reasonable amount of time.
Or I guess like my question is, since we go like from left to right, so we just like look at which like edge is the minimum instead of like the painting houses where you go from right to left and you like look at the total minimum. And like the only reason you can go from left to right, even though like in the painting houses we didn't do that because there could be like an extremely expensive
Yeah,
cost at
yeah.
the end, is because of the priority queue.
Um, it's a little bit of a philosophical question.
Oh,
So the thing of it is that you're right. You could think of figuring out the shortest path in the same way that we thought about houses. It would be a different algorithm than Dijkstra, though. You could think about, and so this is called so like you can do shortest path with dynamic programming. It's kind of a separate algorithm. Dijkstra is kind of a different philosophy, right? So with Dijkstra, it's like because of the mathematical trick, you actually can know which node to add next so that you won't regret adding it, right? So because like the algorithm for Dijkstra, let me just pull it up. So, the algorithm for Dijkstra, right, is that if you have a set of nodes that you visited, then you know that if you add the next node, if you visit the next node in such a way that the path from S to U plus the edge UV is as small as possible, then it's true mathematically that the distance from S to V, the shortest path is from S to U plus UV, and you won't regret it later, right? So if you remember, like that was like the point of the proof is that it cannot mathematically happen that actually like from S to X, then from X to some unvisited node Y, and then from Y to V is shorter than from S to U to UV if you're adding the V's in this particular order where the next V that you're adding is such that from S to any U to and then plus UV is as short as possible. So Dijkstra specifically exploits this kind of mathematical trick where if you select the next thing in a strategic way, you will not regret it.
but say if like there was no connection between Y and V,
Mhm.
and then you like kept on going, and then eventually say like there's a bunch of different nodes in between like X and Y and U and V, and then Y points to like H, and then V
Oh
points
yeah,
to
yeah, yeah.
H.
Like that's the point of the curvy thing is that it's not necessarily a direct edge. Yeah. So like we like mathematically proved that actually like yeah, like that there could totally be a path from S to something and then to V. It's just that it will be longer than S to U plus UV. And that's specifically because we don't just add an arbitrary v. We add the v such that s to u plus the edge uv is as small as possible. And then, like, it's not obvious, but you can prove that if you add the visited nodes in this specific order, then the distances are actually correct. So there won't be a new path that you will have found that will be shorter. There could be a path, there could definitely, but it will be longer. And the intuition is that, like, you're specifically adding the v such that s to u plus uv is as short as possible. So that means that s to x plus xy for any x and for any y is actually already going to be longer than s to u plus uv, because if it were shorter, then you would add y first rather than v.
Okay. Um, so then say if it was like this, and then there was no like curvy arrow between Y to V,
Yeah,
and then you had an arrow from Y to say the node H,
yeah,
and then you
yeah,
also
yeah.
had,
So that's exactly what the curvy arrow means, is that like maybe there is like y to h and then h to v. Yeah.
but then if you're trying to get to the final destination of H,
Hmm.
and then U and V are like the edge is like 1 and 1, and then X and Y is like 2 and 2, but then from Y to H it's like 0, and then from V to H it's like a million.
Hmm.
So then wouldn't you still want to go down SUV because based on like the gray region, then you know that S to U and U to V is smaller than S to X and X to Y?
Okay. So what we're doing with Dijkstra is we are iteratively adding nodes, and then we are right. So we don't have a destination in mind. It could be that if we do have one, then once we reach it, we stop. But
Mm-hmm.
Dijkstra by default just runs for everything. and it
Okay.
and it just like notes down the distance from S to V, and then at some point it will have noted down the distance from S to Y. And then eventually, if you do have a destination in mind, once you know the shortest path to destination, you can just stop before exploring everything else, right? But just because, so like I think what you were asking is like, what if V is not on the way to the final destination? Could totally happen. And that doesn't matter. Like we write down the shortest path from S to V, it doesn't mean that we'll go through V to the final destination.
Oh, okay.
It's just like Dijkstra is about adding nodes in a particular order such that when you're writing down the distance to V, it's actually the shortest path.
Oh, okay. Okay. So then technically, can you use like the algorithm and like way of thinking that we did for the painting the houses for this to
Yes,
find the shorts? Yeah.
yes,
Okay.
yes, you could. So that would just be a different algorithm, but yeah. So that's like not like that would take kind of like some minutes to talk about, and that's just like an algorithm that we didn't do. But
Mm-hmm.
yeah, so like the idea that you could use is that if you have a specific destination in mind, right? So if you are talking about going from S to Y, let's say, right?
Mm-hmm.
And the length of the minimum path from S to Y is the minimum over all the intermediate nodes. So like it's the minimum of like S to X plus X to Y and S to U plus U to Y and so on.
Mm-hmm. Okay. Okay.
So it's just as like it's a different algorithm, right? So like
Mm-hmm.
Dijkstra is like a specific trick where you actually can, in this particular case, and I think that's kind of what you were asking originally about with the houses,
Mm-hmm.
right? So like Dijkstra actually allows you to not ever think back and like regret things
Mm-hmm.
because you're using the specific strategy of like going along the graph.
So if Dijkstra explores all the nodes, does it explore all the possible choices or no?
No.
Be
So all the possible choices, like so I think all the possible choices you're referring to, like all the possible,
yeah.
right?
Uh-huh.
There could be potentially like a lot of other possible paths. Like if
Yeah.
everything is connected, then there's like n to the n
Mm-hmm.
possible paths, so like a lot.
Mm-hmm.
So Dijkstra is a specific technique that works specifically for short paths where you don't have to explore all of them,
Okay. Got it. That
or
makes sense.
in a general case, yeah. So this is like specifically like that's kind of the cleverness of it, is that like it does something more clever than like trying all the possibilities.
Mm-hmm. Okay, that makes sense. Uh, yeah, I think that's basically all my questions
All
for
right,
now.
cool.
Are you also still gonna have office hours at 6?
So that's actually Nick rather than me, who's
Oh,
doing the
right.
6 p.m. ones, and I think he's gonna have something prepared. So I can like also come back online if you like comment and say that you have questions. Yeah.
Okay, cool.
Yeah.
Okay.
And like I assume that he's also gonna like stay for questions, but I think he's gonna have something prepared.
Yeah, I think I saw that post.
Mhm.
Okay, cool.
Yeah.
Okay. Thank you so much.
Yep. Okay. Cheers. Bye.